So welcome to our SPI Doppler review series, and in this section we're building Doppler from the ground up, starting with foundational principles of fluid dynamics and blood flow. So before we touch the Doppler equation or spectral displays, we must first understand pressure, resistance, viscosity, and how blood actually moves through vessels. So in this episode, which focuses on phase one, it'll be fluid and circulatory foundations. And these are the essential concepts that make everything else in Doppler make sense. Now that we've introduced the goal of this series, let's look at the roadmap. We'll begin with phase one, fluid and circulatory foundations. And this is where we ground ourselves in the basics. What a fluid is, how blood moves, and what pressure and resistance actually mean. Once we understand how blood behaves, we move into phase two, which is flow types and patterns. Here we'll examine laminar, plug, pulsatile, and turbulent flow because Doppler really is just measuring how these patterns behave in motion. From there we transition into phase three, hemodynamics and equations. This is where physics steps in. Continuity, Pasquale's law, Bernoulli, the rules that govern flow. With that foundation built, we're ready for phase four, which is Doppler fundamentals. Now the Doppler effect and Doppler equations start to make sense because we understand what's actually moving and why. Next comes phase five, spectral, Doppler, and signal processing. We'll connect physics to what appears on the screen. FFT, spectral broadening, and waveform interpretation. Then we move into phase six, instrumentation and controls. This is where we examine pulsed versus continuous wave, PRF, wall filters, sample volume, and how machine settings affect what we measure. Finally, we end with phase seven, Doppler modalities and clinical application, bringing everything together and applying it to real imaging scenarios. Each phase builds on the one right before it. So we're not memorizing isolated facts. In this review, we're constructing a system, and today we begin with phase one. Now, as we move through each phase, we won't just be reviewing content, we'll be working through sample SPI style questions together. For each phase, we'll take carefully selected questions and dissect them. Not just identifying the correct answer, but breaking down why it's correct, and just as importantly, why the other answers or other choices are incorrect. Because success on the SPI isn't just about recognizing the right option, it's about understanding the reasoning behind it. And when you eliminate distractors with confidence and explain the concept in your own words, that's when you truly understand Doppler. So in this series, we are not memorizing, we are analyzing, thinking critically, and building exam level understanding one phase at a time. Okay, let's go ahead and get started with the first question. The following, which matter is considered a fluid? And the answers provided are gases, solids, liquids, and D, which is gases and liquids. So again, the correct answer here in physics, if we go by the definition of a fluid, is any substance that can flow and continuously deform under shear stress. And this would include liquids and gases. So both, right? Both of these do not have a fixed shape. They take the shape of their container. They flow when a force is applied. So even though we often casually think of fluids as liquids, scientifically speaking, gases are fluids too. And that's why airflow and blood flow are studied using these same fluid dynamic principles. Now, this is an easy question, but I'm going to go through the protocol that we said about discussing why the other answers are not correct or not the most correct. And so again, A says gases, and so gases are fluids, but the question asks which matter is considered a fluid, and the most complete answer includes both gases and liquids in this question. So choosing only gases ignores liquids like blood and water, which absolutely behave as fluids. So A is just incomplete. When we look at B, solids, well, solids are not fluids. And why? Again, going back to the definition, solids have a fixed shape. They resist deformation. They do not continuously flow when a small shear force is applied. If you push on a solid, it may bend slightly, but it doesn't keep flowing like a liquid or a gas would. So solids do not meet the definition of fluids. Then we get to liquids again. Liquids are fluids, but again, incomplete. This answer ignores the gases. So in medical physics, especially ultrasound and hemodynamics, we apply fluid principles to both blood, which is a liquid, and air, for example, which is a gas. So C again is only partially correct, which makes it the wrong answer in the multiple choice context. And so again, from here on out, we will be attacking every question in this manner, not only looking at why the right answer is the most correct, but why the other answers are not correct. All right, so the next question is the normal adult circulatory system contains blank liters. And so the normal adult circulatory system contains approximately 5 liters of blood. And that's a standard average for a healthy adult, about 70 kilograms or 154-pound person, like a healthy individual. So where does that number come from? Blood volume is roughly, if we look at it for a 70 kilogram adult, 70 times 70, which gives us about 4,900, and which is in milliliters, which will give us approximately 5 liters. And that's the accepted normal adult value. And why the other answers are wrong. So A says 3 liters, so that's obviously too low. That would indicate significant hypovolemia, which is what President George Washington passed away from. The next one is 4 liters. Now this is slightly low for an average adult. This may be seen in smaller individuals, but not the standard, what we call an average adult male. The next one is 6 liters. This might be a little on the high end, so this could occur in large adults, but not the typical reference value. So again, the question is asking for a normal adult, meaning a healthy adult. So a quick memory trick for this, if you think adult equals 5 liters and an infant is equal to something much, much less, around 80 to 90 milliliters per kilogram. So if you can use something like that, that'll help you determine the approximate blood value for, let's say, an infant. But again, 5 liters is a classic exam number. Okay, so this question says, blank are the tiniest vessels in the human body. And I haven't been doing this so far, but let me start now. I'm going to read the options to you. So A is veins, B is venules, C is arterioles, and D is capillaries. Now, obviously, the right answer for this one is capillaries. And capillaries are the smallest blood vessels in the body. They're about 5 to 10 micrometers in diameter, and often they're just wide enough for red blood cells to pass through single file. They're only one cell layer thick, so they're endothelium only. And that has a lot to do with their function, which their job is to exchange oxygen, carbon dioxide, nutrients, waste products. And because they're so thin and tiny, diffusion occurs very efficiently with this tissue. So when you see a question asked for the tiniest vessels, that should automatically trigger capillaries if it's in one of the options. Now let's go ahead and look at the others and figure out why we should eliminate the others. Now A said veins. Now, veins are much larger vessels. They carry blood back to the heart. They have larger diameters. They have valves. That's another feature for veins. Not much to do with its size, but just another piece of information. But they're definitely not the smallest. Now, when we look at venules, again, the word venules, the suffix means pertaining to something being small, so it's a small vein, but they're definitely not the smallest. Right? They're small vessels that collect blood from capillaries. They're larger than capillaries. They're structurally thicker. So think of venules as the drain pipes leaving the capillary bed. Arterioles, here's another word with the suffix IOLES, that means small, right? So not to be confused with the small s in the list. So yeah, this is one of the smallest arteries, but again, definitely not the smallest. They're small arteries. And what they do, just a little background, is that they help control resistance, they regulate blood pressure, they have smooth muscle in their walls, just like all arteries do. They are much larger than capillaries though, and they play a big role in vascular resistance. but again, they are not the tiniest vessels. Even the word arterioles means a small artery. Okay, so this question asks, gases, nutrients, and waste products are exchanged through the walls of blank. Again, the answers are, or the options are A, arteries, B, venules, C, arterioles, and D, capillaries. So again, the correct answer is capillaries. Capillaries are the exchange vessels of the circulatory system. They're specifically designed for gas exchange, meaning mainly O2 and CO2. They also are also used for nutrient delivery. These are things like glucose and amino acids. They're very useful for, or their function, not useful, but this is part of their job, is waste removal. So this means removing CO2 and metabolic byproducts. And they also help fluid shifting. So why capillaries? So a little review, a little fun, AMP for capillaries. Again, we mentioned before they're one cell thick walls. Again, they're just endothelium tissue. They're extremely small diameter, so they have very slow blood flow, and they have a huge total surface area. So that thin wall allows diffusion to occur easily. So its function is based on its anatomy. And so this is literally their job. And why the other answers are wrong. This question might seem very simple to you, but again, I'm going to go through the protocol that we established for how we're going to study for this review. So let's go ahead and dismantle the others, which we will call distractors because they're distracting you from the right answer. So answer A was arteries. And what are arteries? Well, think about it. Arteries, they carry blood away from the heart. They have thick muscular walls, and they're built to withstand high pressure. Their walls are way too thick for any kind of efficient diffusion, and they're like delivery highways. They're not unloading docks. The next answer was B, venules. Venules, again, the ULES means that it is something small, but that's not what this question is asking. But their job is to collect blood from capillaries. So they're not like the next smallest thing. And they begin that return trip to the heart. So some minor exchange can occur in very small venules, but they're not the primary exchange vessels. And they're more like cleanup collectors after exchange has already happened in the capillaries. The other answer was arterioles. Now again, these are used to regulate blood flow in capillary beds. They help control blood pressure. Again, they contain smooth muscle for vasoconstriction and dilation. And they're like, not that they're valves, but they're like control valves to help regulate, again, blood pressure and fluid exchange at the sites. So their walls are still too thick for any kind of meaningful diffusion because of that muscular wall that they have. And a quick clinical memory trick for this, if you're looking at the vascular tree, think of arteries as transport under pressure. Arterioles, think of them as the things that control flow. Capillaries are used for exchange. Venules are used to collect. And veins are used to return blood back to the heart. And again, only one of those is built thin enough to allow oxygen to slip across the membrane. Okay, so this question asks, the resistance of the blank accounts for about 1/2 of the total resistance in the systemic circulation. And the correct answer here is going to be the arterioles. Remember, arterioles are called the resistance vessels for a reason. They account for about 1/2 of the total systemic vascular resistance, SVR. And why arterioles? So let's talk a little bit about AMP for arterioles. So arterioles have thick, smooth muscle walls. They have small luminode diameters. They have the ability to vasoconstrict and vasodilate. And here's the key. So if you remember the proportionality for the equation, resistance is extremely sensitive to radius. So where resistance is equal to 1 divided by the radius to the 4th power. So even a tiny decrease in arterial radius causes a massive increase in resistance. And they're the primary regulators of blood pressure, blood distribution, peripheral resistance, and that's why they contribute to about 50% of systemic resistance. And so why are the other answers wrong? So the first one, A, says blood flow. Blood flow is not a structure. So it's just a result of pressure divided by resistance, and you can't assign resistance to blood flow. The second one, B, is flow rate. And so flow rate is a measurement. It's not a vessel again. Resistance affects flow rate, not the other way around. And then D is capillaries. So capillaries is a structure, and this one may trick people. So capillaries are tiny, so shouldn't they have some high resistance? And individually, yes, they do, but there are millions of capillaries arranged in parallel. So parallel circuits dramatically reduce total resistance. So even though each capillary is small, the overall capillary bed resistance is much lower than arterial resistance. Again, this is a physics phenomenon that's not just true for blood flow. This is true for any kind of flux. It could be electron flux, electron flows, what electrical engineers would say. So it's a universal concept. And the clinical connection that we can make here is that when blood pressure rises or falls rapidly, either way, it's usually due to changes in arterial tone. So they are the control valves of systemic circulation, not actual valves like within the venous system, the veins. All right, so let's look at this next question. It says, the state of the downstream arterioles is reflected in the blank. And so this would be the correct answer. Oh, I'm sorry, I'm supposed to be reading the options. So option A is arterial peak systole, B is arterial diastolic flow, C is venous flow rate during expiration, and D is venous flow rate during inspiration. So the correct answer in this case would be B, arterial diastolic flow. And the key idea here is peripheral resistance. So arterioles are the primary resistance vessels. They control how much blood can pass into the capillary beds. And so you can think about the cardiac cycle as systole, where the heart contracts and you have a strong forward push. Diastole, where the heart relaxes, you have a forward flow that depends on downstream resistance. And if arterioles are dilated, you're going to have low resistance or lower resistance. So blood continues flowing during diastole, and you'll have high diastolic flow. If the arterioles are constricted, you'll have, relatively speaking, high resistance. And so this leads to flow drops during diastole, so low or even reverse diastolic flow. So the waveform portions that reflects the condition of the downstream arterioles is diastolic flow, and that's why peripheral resistance is assessed by looking at end diastolic velocity. Now let's look at the other answers and why they are not the most correct answer or completely incorrect. And the first one was arterial peak systole, right? Peak systolic velocity, PSV. And this mainly reflects cardiac output, the strength of the ventricular contraction of the heart, the proximal stenosis. And so systole is driven by the heart's force, not downstream resistance. Arterioles influence diastole more than they do systole. So this answer focuses on the wrong phase of the cardiac cycle. The other answers that was incorrect is C, which is venous flow rate during expiration. So venous flow patterns are influenced by respiratory variation, right atrial pressure, thoracic pressure changes, and they don't directly reflect downstream arteriolar resistance. And so this mixing venous physiology with arterial resistance doesn't work. And the other answer that was incorrect was D, the venous flow rate during inspiration. And we have the same issue here. Venous flow varies with breathing due to pressure changes in the thorax and the abdomen. And this has nothing to do with the state of the downstream arterioles in the arterial system. All right, on to the next question. So the next question says or asks, what is required for flow to occur? Answer A is hydrostatic pressure. Answer B is pressure difference. Answer C is constant driving pressure. And answer D is variable driving pressure. So the correct answer here is B, pressure difference. Flow only occurs when there is a pressure gradient, meaning blood moves from higher pressure to lower pressure. Now, this is true, again, this is a physics concept that is universal, true for everything. Flow happens when you have something moving from a higher concentration gradient to a lesser concentration gradient. And in this case, we're talking about pressure. So if you have no pressure difference, there's no movement. So this is true for blood flow, airflow, water in pipes, IV fluids, basically all fluid dynamics. So the fundamental equation behind this is that flow is proportional to the difference in pressure divided by the resistance. So if the difference in pressure, or delta P, as you learned in your physics course, is equal to zero, right? So zero over any resistance as a fraction equals zero. So that's it. That's the end of the story there. So why the other answers are wrong, let's go and dismantle them a little bit. We won't be so harsh. The first one was hydrostatic pressure. Hydrostatic pressure is simply pressure exerted by a fluid at rest. And you can absolutely have hydrostatic pressure without flow. An example would be a full IV bag that's just sitting still. Blood pressure measured in an artery at any particular moment in time can be looked at as hydrostatic pressure. So pressure just existing does not equal pressure difference. You need to have two different pressures. We do this in electronics all the time. When you measure voltage, it's from a reference point. Voltage being the analogous to pressure, you need a difference to have a potential difference, is what we say in electronics. Again, a universal physics concept that applies across all engineering disciplines. The other answer that was incorrect is C, the constant driving pressure. So flow does not require pressure to be constant. In fact, blood pressure is pulsatile. So flow still occurs. So pressure can vary as long as there is a gradient. So constant is unnecessary. And the last answer that was incorrect was D, the variable driving pressure. This is also incorrect because variability is irrelevant. Pressure can be constant or variable, and that's not the requirement. The only requirement is one area must have a higher pressure than another. So to kind of summarize this and clean all this up for you, to get flow, you need 2 points, you need 2 pressures, and a pathway between them, and that's it. So if pressure equalizes, flow stops. Again, universal concept. When you measure an EKG rhythm, you're measuring between 2 points. Okay, let's go to the next question, and that is, what is the driving force behind blood flow? And the answer options are A, the heart, B, gravity, C, pressure, and D, flow rate. Now, we kind of talked about this already, but let's continue going into it into more detail from the perspective of the concept of this question. So the correct answer is C, pressure. So blood flows because of a pressure gradient. So flow always moves from an area of high pressure to an area of low pressure. And the left ventricle creates high pressure. The arteries have high pressure, higher than the arterioles, and capillaries have higher pressure than veins. The pressure difference is what drives that movement. Again, if you have no pressure gradient, you have no flow. Even if the heart exists without a pressure difference, blood wouldn't move. So let's go ahead and look at the other answers and why they are incorrect. So the first one, A, it says the heart. So again, this one's tempting, right? Yes, the heart creates pressure, but the heart itself is not the driving force. The heart is the pump. Pressure is the force. So think of it like this. A water pump doesn't push water because it exists. It pushes water because it creates pressure. So the heart is the source of the pressure, but pressure is what actually drives the flow. B, the other incorrect answer, which is gravity. Now, gravity affects circulation, especially venous return, like in the legs, but it is not the primary driver of systemic blood flow. So in fact, we can lie down flat and blood still circulates. Astronauts who are in microgravity still have circulation. So gravity influences flow in some situations, but it is not the fundamental driving force. The other answer that was incorrect, D, which is the flow rate. Again, flow rate describes how much blood is moving per unit time, but flow rate is the result of pressure and resistance, not the cause. So remember the relationship that flow is equal to pressure divided by resistance. Flow doesn't create itself, it happens because pressure overcomes resistance. Okay, so the next question is, I'm sorry, I have to lean in to read the question on the slide here. Resistance to flow offered by a fluid in motion describes, and the options available are A, velocity, B, pressure, C, viscosity, and D, volumetric flow rate. And so the correct answer here is viscosity. Viscosity is a fluid's internal resistance to flow. It describes how thick or sticky a fluid is. So something like honey has a high viscosity. It flows slowly. It resists motion. Water, on the other hand, has a low viscosity, so it flows easily. Blood has measurable viscosity that affects circulation. So it's literally the fluid pushing back against motion. So when the question asks for resistance offered by the fluid itself, viscosity is the only answer that fits. Now the other answers that are incorrect, the other answers are incorrect, so let's go over them one at a time. And the first one was A, velocity. So velocity, again, describes how fast something is moving. It's a rate. And it describes also in what direction. So it does not describe resistance. Velocity is the result of forces acting on fluid, not the property resisting movement. Think of it like this. So viscosity affects velocity, but velocity does not describe resistance, if that helps. The other answer, B, pressure. Pressure, again, we've talked about this as the force exerted per unit area, and pressure is what pushes blood forward through vessels. So resistance, like viscosity, works against pressure. So pressure drives flow, viscosity resists flow. So pressure and resistance are opposite roles in fluid movement. I'm thinking of something that's happening in my car right now, and I should probably take pictures of it and show you what's happening. I'll discuss it right after this slide though. So D, volumetric flow rate, that's incorrect because volumetric flow rate describes the volume of fluid moving per unit time, and that's usually written as Q, and it tells you how much fluid is passing through a vessel, not what is resisting it. So again, viscosity influences flow rate. Flow rate is not a form of resistance. Now, I was talking about answer B, pressure, right? So pressure is what pushes blood forward through the vessels, and resistance, like viscosity, works against pressure. So in my case, my oil lamp is on, indicating that I either have low pressure or high pressure according to the sensor. Otherwise, what it's telling me is the pressure of the oil is not within the tolerances of what it should be. So it could have either thickened up, maybe some of it burned off and it's just thickening up and I need to change it. Or it could also mean that I don't have a pump that's creating that pressure. So that could actually mean something worse, that my oil pump is not working, creating pressure, so the sensor is not detecting the right pressure. So I'm going to have that. I'm going to try to fix that this weekend, and I'm probably going to take some pictures and add that to this slide here or this review, so you can see that this concept isn't just about blood dynamics. It's about any fluid dynamics. Okay, and then learn how to read your oil pressure sensor lamp. Okay, so the last question for these basics and fundamentals is this. Poise, right, pronounced with like a Z, P-O-I-S-E, but it's pronounced like a Z. I looked it up to make sure. It's French. Poise is a unit given for blank, and the available answers are A, density, B, velocity, C, viscosity, and D, pressure. Now, I know that the correct answer is already highlighted on this slide. And so the correct answer would be viscosity. Poise is a unit of viscosity. And more specifically, it's a unit of dynamic viscosity. So it's in centimeter, gram, second systems. And one poise, designated by P, is going to be equal to 1 dyne second per centimeter squared. And in medical applications, because we're dealing with tiny viscosities, we're looking at centipoise, right? And so something like blood viscosity would be 3 to 4 centipoise. And why are the other answers wrong? Just by units alone, we can look at this. So the A was an option, density. So density, if you remember from physics, is measured in grams per centimeter squared or kilograms per meter squared, right? So that's mass per volume there. So that's not poise for sure. B is velocity. Again, velocity is measured in some distance per time, so centimeters per second, meters per second. If you want to think of miles per hour, again, that's some distance per time. So poise has nothing to do with speed. The other answer that was incorrect was pressure. So pressure is measured in millimeters of mercury, in pascals, or in dynes per centimeter squared. Sounds close, but again, not poise. So a quick memory trick. Oh, my camera light went out in the room, but I think you can see me better. Memory trick. So P is for poise, and it's designated with the letter P, and that just means it stands for the thickness of the fluid. So honey, for example, has high viscosity, it has higher poise. Water has low viscosity, has lower poise, and blood just sits in between those two. And thank you very much for listening to the first part of this review, phase 1, and I'll see you on the next phase of our study review for specifically only Doppler of the SPI exam.